Chris Jordan with No Fisheries at the Science Center, our new office in Corvallis, which is me. I'm hiding from the traffic in Seattle. Leska said we should stop talking about traffic in Seattle. But, okay, so what I wanted to talk about, and Greer already introduced the topic of thinking about lifecycle models and IMWs. And so this is a loose collection of thoughts. And initially, Amy and Jen said, you should have an hour for this. And I pushed back on that. And now that the time has gone on, there's more appropriate level of time, about a half an hour. I'll give you some information. Hopefully we can have a conversation. Because I do think this is bringing these tools together. I think of these as complementary management tools. This is an emerging collaboration, unstructured at this point. Okay, so 2 years ago, I gave a talk at this IMW conference. It was supposed to be on gaps in the future in IMWs, and I featured the Middle Fork John Day IMW. So here's a picture of the location. You've heard about this before. There are implementers and managers, past and present, in the room. The Middle Fork John Day is a collection of actions that have been put together into a form of an IMW. This is a set of projects that moved into the IMW label, or the IMW label was attached to it, whether they liked it or not. But it was a way of coordinating the actions and adding monitoring to it, which I think in the end was a good thing. What I was focusing on the project, though, was what was done with the opportunity to have a large-scale restoration project with lots of monitoring. And I talked about a way in which habitat characteristics were measured, documented in the John Day, in the Middle Fork IMW. And this is just a series of overlays on top of a DEM topography of one reach, as just to remind me to talk about how the process is of going from taking physical habitat and turning it into the currency of fish. And so moving from the left-hand side, well, here's the DEM and the fish currency of a reach before it's been restored. Here are hypothetical wood projects that are put on there. Here's the hypothetical change in topography of that reach. And then asking what's the new distribution of flow. Here's a flow model, depth and velocity. And what's the new resultant value of that habitat to reach to fish in terms of capacity from a bioenergetic standpoint. And the fact that this can be done at a reach is really cool, but what's that got to do with an IMW? Well, if you can take this before treatment and after and scale that up to an entire watershed, then you can ask questions of what's the value of doing projects, whether you've done them or not. In a sense, you're doing the project in the computer, and you can scale up the value of those projects. And this is just a picture of that process of going from the dot, where data is collected to the entire network. The colors of the line work in the network is the fish value. And you can put this together into a lifecycle model, because these, now what we've taken is projects that are on the ground, their projected benefit at the scale of a watershed, at the scale of a demographic unit, and you can ask what are the population dynamics of fish, in this case steelhead, in that watershed, and with a lifecycle model. And here's just output predictions from the lifecycle model. The top is abundance, the middle is productivity, and the bottom is called an extinction risk for 4 different scenarios. And I advanced this as the best example of an IMW because it had a lifecycle model. And Jim Rosicki was cringing in the back because he had brought IMW to the table as one that was really struggling and needed help from the collective. And here I was, not on message, and say the IMW in Middle Fork John Day is the most advanced IMW because the information was put together into this management tool of a lifecycle model, because these are scenarios that aren't necessarily implemented. These are the full implementation of the project. These are some assumptions about what would the benefit of the project be and asking what's the biological difference. And that is a generator of hypothesis at the scale of a watershed. And it's only possible because of that level of integration of both the data collection, the implementation of projects, and turning it into this quantitative tool like that. So to me, I brought this up to the group as being what I think is the sort of the next generation where IMW should go. And so that's what I think, and the topic has been brought up already. What is the value of linking lifecycle model predictions within the IMW framework? So I can see a number of them, and I'm just going to give you some examples of them, and hopefully we can have a conversation about them. So I just showed you an example of forecasting outcomes across multiple action strategies. So the game that's being played on the implementation game is not being on the ground and waiting decades. It's taking what we know about fish habitat relationships, scaling it up to population, what we know about demographic processes, and running out those scenarios for 50 or 100 years and saying, what is the population, long-term population abundance, and what's the extinction risk under these different assumptions of what's going to happen to habitat. That allows you to evaluate the potential efficacy of different strategies. It points to holes in your knowledge of translating those actions into fish responses. It allows you to play this game. You know, what if? In that particular scenario, what if this shade had this effect on stream temperature versus this effect, right? Or if only we could do this kind of work, this is what the benefit would be, right? So I see this as a communication tool. It's a learning tool, but it's also a communication tool. And something that's come up already a couple of times is trying to extend this learning beyond IMW bases. So IMW bases are one of the reasons for IMWs in the first place. Wasn't necessarily around restoration experiments. They were places where we had dense enough monitoring that we could ask fish population questions. Because what we know about salmon life cycles requiring a large freshwater area to ask questions of what is the survival benefit, how do survival benefits change entire population trajectories. You can't do that at the reach scale. You have to do that at the demographic or the population scale. You have to do that with sufficient density of monitoring in order to collect the right data. Now you have the watershed and the intensive monitoring part. Without the manipulation, without the experiment, some IMWs, some conceptualization of IMWs you start with, we're really just trying to get at basic fish biology that has to be done at an intensive watershed scale. So which means you can't do it everywhere, you shouldn't be doing it everywhere, but how do we extend that learning? I think that lifecycle models are a tool to take in common fish biological processes and apply them in different landscapes. I want to show you an example of that too. Okay, so what if or if only question. Here's the NPS IMW Implementation Plan. You've heard about the NPS. You have heard about it before. The NPS IMW broke. Here's the confluence of Columbia. The NPS is broken into geomorphic valley types and channel sections, and an implementation schedule for treatment. So the controls, the restoration, internal controls, never treated across the different regions, was scheduled out for a decade. The implementation of the project stopped somewhere in here with the actions and the monitoring. But there was some information generated. There were actions done. There was an awful lot of fish monitoring, habitat monitoring. But what didn't play out in the overall experiment is what is the effect of all of these treatments. So that you took all of, basically you saw the green regions pre-treated converting to red as treated. This is a hierarchical staircase experimental design. So treatments became, controls became treatments through time, except for the never treated internal controls. So it's a very complicated physical design with that. So out of that design would have emerged a biological answer had you put all of the information into the design and just done all the treatments. That didn't happen. Is it a waste then? Well, it's not a waste because, nothing new there, because you can take that information and simulate the population response. And so here is a bunch of futures for Chinook populations, so these delta statement, mean statement, long-term average, based on a number of scenarios of what would the effect of restoration be. So increasing capacity, juvenile rearing capacity, and the number of top these boxes is a survival term. And the restoration that would be done would have gotten to about, sort of, here's the baseline here, and would have gotten to somewhere in this range here, about 1% or so change in capacity and 1 to 2% change in survival, because there's only a small amount of the over. This is a watershed case, right? So they're that average level. But have the project been able to proceed, and were those actions actually beneficial? So you'd expect a larger change in capacity and potentially larger change in survival. And the black line here, that's the TRT recovery threshold, the small R recovery threshold. And the population size is well below that now. But the level of change of those biological processes is not unreasonably large to get there, right? So we're talking, so 5 or so for the screen, several percentage changes in survival or several percentage changes in capacity to be getting across this line. If you want to have high confidence that you can cross that line, mass of this, of that box moisture plot, more like 5%. The changes in habitat that were implemented from an initial change and initial restoration actions were about 1% change in capacity. So obviously more actions are needed, but not an unusual amount. So what this does is say, allows us to ask the question, how far do we have to run some of these large experiments before we have enough information to try to reject the future? This is a hypothesis, right? There are a lot of assumptions about how fish will respond to habitat and how habitat changes in time. But this is basic machinery of taking what we've learned in large-scale experiment and turning it into a future projection. I'll show an example from the Grand Ronde. So this is the work of our earliest part of Tommy, who's retired, not passed away, in the Grand Ronde. And Tom is working with IMW and CRISPIC, who have a long-term monitoring of both habitat and fish population, and trying to integrate that information into a lifecycle model with strong focus on what the restoration action in the upper Grand Ronde, and Catherine Creek Chinook populations. And can we project the value of habitat? So using some sort of a prioritization scheme that's developed from local implementers of how they would like to treat the watershed. And thinking about long-term, not just short-term actions, but really long-term, decades worth of things that will either take to get on the ground or that would realize the benefit. And what was cool about the work that Tom's doing, still doing here, is that he's thinking about how restoration actions themselves evolve. There's a time history of action. So their benefit accrues, and then it might even fade away. And so you can build that. So this is a temporally explicit life cycle modeling tool, and the kind of actions. I'm going to get before I'm done. I'm going to get the directions right. Down. You got to go down to go forward in time on the computer. Habitat implementation schedules have different types of actions, whether they are the recovery plans, flow and channel restoration actions, the Grand Ronde Valley modifications, so the changes in survival and migration timing phase, and then very long-term channel and riparian restoration, mainly involving the reconfiguration of the safe ditch and the main channel of the Grand Ronde and how Catherine Creek connects into that. So these are very long-term and if only kind of questions. Can you really get to that restoration? And then ask the question, is that really going to matter? How is that going to play out? And so Catherine Creek, Grand Ronde, two populations of Chinook. So here's the past conditions. Again, we're talking about the abundance. We have a year 50 from in the future. Some past habitat actions. There's a little one. Here's some estimates of what the benefit of operations of hydro systems. So let's just ignore all of those. But here's long-term actions relative to current actions. And here's the what if. Really long-term, I really wish we could get these kind of actions on the ground in Grand Ronde. Those are the kind of benefits. So here is looking at the relative magnitude of very different management strategies, whether it's hydro system, different kinds of restoration, and need to have those priorities. You need to have that potential goalpost in mind to motivate the discussions and all of the conversations would have to go on to accomplish some of these long-term or really long-term. This is really going to change how people use the landscape in order to achieve that. So why would you enter into that conversation? We were having a conversation earlier this morning about engaging with landowners. This is what suggested to be the benefit by going that route. You can do that by projecting the populations with these life cycle models that are based on a lot of local biology, and in this case, a very time-intensive, sort of temporally explicit set of simulations. And the last example I want to talk about is more sort of spatially explicit and extensive, extrapolating these things to places where we don't have that. So here are Chinook populations in the upper salmon, Chinook, MPG, all the way up into the salmon basin here, Tiburon, Lehigh, some of the places that you may recognize the names of. For this landscape, there is characterization of reef habitats at a very detailed level in some places, and at a very, not crude, but superficial first pass level elsewhere. And in some places, just a GIS expansion of that information. There's good fish monitoring in some of the populations and not in others, and others, like panther, is listed as extirpated because of past mining activity. So what would potential restoration strategies look like? Here is taking the fish biology we have in other places and playing on a landscape where we don't have this kind of IMW investments, and is that worth it at all? And I have just a set of slides that characterizing. So the landscape here's the Lehigh, reef typing has been done across all of these watersheds at some level. The value, sort of the condition of those reaches of different flavors has been done, again, at different levels. And we have documentation of where restoration actions have been done in the past. We've got our in-stream actions that have happened from 2009 to 2015. So one question we could ask is, what's the benefit of those actions, in this framework? And then, what would the benefit be of putting more actions like this across the landscape? And this is more of a spatially explicit approach, and trying to extrapolate that to watersheds where we don't have that information explicitly. We do have the backgrounds or the extensive information in terms of channel classifications for all of these populations. We do know where actions have happened. And we can run it through a life cycle model, and you get these kind of figures. Each of these set of three of the populations, or 8 populations, you can't read this text. That's not on purpose. Here is a sort of baseline pre-2009 estimate of the population. Here's an estimate of the population, each for each of these populations, based on here actions that happened between 2009 and 2015. And here's the future, these 3. And in these 3 cases, what I did is I just said, I want to improve 1%, 5%, and 10% of the habitat annually. I'm just going to grab reaches randomly, not necessarily good or bad, but just randomly. So this is actions that are happening across the landscape that you didn't have any control. And you can see, in some cases, there's beneficial by just doing these. In some populations, it doesn't really seem to be a big difference by doing a lot more activities. So the populations respond differently. But what if you were intentional about your actions? And so for 4 populations, I just played a game by saying, I'm only going to improve good habitat. And so that's what these are. Here's that baseline, here's the 9 to 15, here's my random actions. And here's about middle level of effort, where I'm intentional. I'm going to pick good habitat. And so the point of this being to have this sort of spatially explicit view of the future is asking, can I actually project that it is useful to plan food restoration? That is, again, the hypothesis generating process. But differentiating between these random actions and intentional in 4 different populations, it looks like, yes, planning actually matters. Maybe we already knew all that, but now we can try to quantify the benefits to which planning matters, and this is part of the communication loop, where you can take some output from the science, pass it through another process by which we're distilling it, and make a message that we think might be useful in a communication. Okay, so take-home message. Why not use lifecycle models in conjunction and conjunction with IMWs? I don't know, why not? What was the downside? I think that there's a population estimation benefit. You can generate temporally and spatially explicit hypotheses to test with your IMWs. And if you're going to do it at the end, or if your funder says you have to do it at the end, it's necessary to be able to project into the future to generate quantitative hypotheses and testing. And we do not have a way of doing that short of using a lifecycle model. So if we integrate these tools, we can really start doing that in management in large scale. Okay, that's what I got.